Hey guys, let's start off this unit talking about current electricity, about current that flows, and Ohm's law, which is a big deal in electricity. Okay, so different from static electricity where charges stay put and build up a field, cause that kind of stuff, we're now going to talk about flowing of electrons, okay, in a conductor, usually copper or aluminum, things of that nature. The definition of current, electric current, is the amount of charge, which we're really talking about electrons, that occur in a certain amount of time. So current is coulombs per second, which coulombs per second is amperes. So here's the formula. I, the symbol I is used for current. Q is still used for charge. Again, it doesn't matter lowercase q or capital Q because I sometimes use both. And time is seconds. So coulombs per second is the definition of an ampere, or we call them amps. If we're going to use one of the circle formulas, just so that we start using these, so we're going to have Q, I'll use capital, equals I times T. So remember, when we use the circle formula, if you want to solve for charge, you multiply I times T. If you want to solve for time, you cover it up, it's Q divided by I. If you want to solve for current, it's Q divided by T. Those are just, we're just going to put these in because there's a number of formulas in this unit that make themselves amenable to circles. So find the current that flows when 4 times 10 to the negative third coulombs flows in 4 seconds. So I is Q over T. We're going to have 4 times 10 to the negative third, or milli coulombs, over 4 seconds. Well, you can do that in your head because 4 divided by 4 is simply 1. It's 1 times 10 to the negative third, capital A for amps. Now, 10 to the negative third is for prefix milli, which is really 1 milliamp. Milliampere. It's technically ampere, but that's what it stands for. That's a very common measurement. There's also microamps, so not so many nanos and things of that nature. So that's just a definition of what current is and how it's found. So most times we're going to be looking at some kind of circuitry where we have wiring and things. And Ohm, this gentleman named Ohm, investigated that when you put a certain amount of voltage, voltage is like the push to electrons. Resistance is the opposition to the flow, and the flow is current. So resistance is the opposition to the flow of electrons. He found that certain electric devices retain their resistance. In other words, even if I increase voltage, the current will increase. If I decrease voltage, it will decrease, and the resistance will remain the same. Resistance is measured in a unit called ohms. We use the Greek symbol omega to represent it. Voltage is measured in volts. Voltage is also, remember, called difference of potential, or potential difference. And then current is measured in amps. So if it's in milliamps, we have to convert it. Okay, if we're going to make a circle formula for this one, it's V on top, I, R. So if I'm going to find voltage, it's I times R. If I'm going to find resistance, it's V over I. If I'm going to find current, it's V over R. So for example, I have a wire is connected to a bulb with a voltage of 6. So volts are 6 volts. The current through the bulb is 200 milliamps. Now, I already did this over here for you, but to go from milliamps to amps, I'm dividing by 1,000, and that's how I get 0.2 amps. So I always want to use it in amps and not milliamps. So resistance is my question mark. All right, well, you can use the circle if you want. I can cover up the R. It's V divided by I. Okay, so R equals 6 over 0.2. 6 divided by 0.2, just type it in your calculator, is 30 ohms. That's how I draw omega. Okay, so it looks like that when you take your time, and when you're fast, it kind of looks like that. So work on that in your Greek letters. So one of the things we have to learn about circuits is how to put them together. So there's something called a circuit schematic. Sorry, I'm going to move some of my stuff out of the way I have here. And in that case, you're going to learn some symbols. So this symbol that has a short line and a long line represents a battery. Here's a simple 9 volt. On one side's plus, The other side would be minus. Huh, they didn't actually label that. They only labeled the plus sign. How about that? And it's a Duracell. All right. This little guy actually comes from this kind of lamp where inside, I suppose I could bring it up here. I don't know if you can see that. Inside you have the old tungsten filament. Okay, so this would be a lamp or a bulb. You'll also see a symbol that just looks like this with an X on it. Okay, so it doesn't matter if it's a little lamp like this that has some wires, or maybe just a little lamp like this, or one that's just in your house. Doesn't matter. All right, a straight line just refers to a wire, any kind of wire. Here's some wire right there. Doesn't matter what color, that's irrelevant. Okay, with an M, we're talking motor. So here's a little motor. Okay, the connections are down here. Some of them are more specific, and the motor can also be used for things that just have a motor in them. Like here's a fan taken out of a, I guess it was an old computer. You can see the fan blades, they spin. I haven't hooked it up to anything. It hooks up to 12 volts, but that would also be allowed as a motor symbol. A resistor, which we're going to spend a lot of time, gets a little triple zigzag. So resistors are devices that are put into circuitry. I should have brought home a circuit board. And they are made to have a certain value. So I'm going to try and zoom in on this bad boy a little bit. Let's see what I can get here. Move it up over here. I guess that's my zoom is up. So there is yellow. There's a purple. I know it's a little hard to see. There's a black color, and then there's a silver. That's one color combination. Here is some noise being made at my house. Just ignore it. So this one, let's see if I can bring it up a little bit. It's very hard to see. There's a gray stripe there, followed by a red, a brown, and then a silver. I know the silver is pretty easy to see. And let's see, I have another one. This one's still in a package. Might be able to see it better. There's a brown, a black, and then a gold. For our purposes, the gold and the silver and the things that we're going to talk about aren't going to really matter for the virtual labs we're doing. I'm so sorry about that noise. It'll stop in a minute. But these are just a bunch of different resistors that have, and these numbers mean different things, and that's what we're going to do on the next page. But that's what a resistor is. They're used in lots and lots of circuits. Okay, there's a couple more here. Okay, if you see these wires with these dots, that is a junction, in other words, where wires connect. And then a broken wire, so it looks like it's a wire that was broken, is nothing more than a switch. Now, this isn't what your switches look like at home. Here's a switch. Oops. And a switch is literally a wire that's broken. So there's metal here, and when the metal doesn't touch, no connection. When you touch it, so inside your house at different places when you have switches on and off, essentially you're breaking a wire, connecting a wire. That's what switches do. Okay, let me zoom back in a little bit, zoom back out. All right, so let's talk schematic. This is a very simple schematic of a simple circuit. A simple circuit has one device in it. This one has a battery. A battery is not a device, it is a power supply. It has a switch. A switch is not a device, it is simply a wire that's broken apart and put back together. The device in here is a light bulb. So when the switch is connected, the circuit will work. When the switch is disconnected, the circuit will not work. So let's talk about electron flow versus current flow. Well, in the battery, what really happens is electrons leave, they come through the device, and they come back around to the positive. That's what really happens. But when electricity was first discovered, and Ben Franklin was working on it, there was a belief that there were positive charges, not protons necessarily, but positive charges, and the circuit would go this way. So it's just two thoughts on this, okay? Conventional current will always go plus to minus, and electron flow will always go minus to plus. We're going to stick with conventional current flow because that's what engineers use for most of their studies with electricity. In order to take measurements, and again, we're going to do it virtual, but these two rules are going to apply, even though it's a little different than when we do it in class on a real lab. When you're going to measure the voltage of, let's say, this light bulb in the circuit, you would never disconnect the circuit. Voltmeters will have two probes, and you will touch one side of each. It says one side of the meter touches positive, the other touches negative, and it looks like this. I'll put a V here. Voltmeters attached to the circuit. And when we get into the lab tomorrow, I'll show you how this works. To measure current, you actually have to cut the circuit. So somehow we actually have to like cut the circuit, and then we put in the meter, put an A. Sorry, that's a really crappy, you would have an A next to it for an ammeter. So voltmeters go like around, if you will. Ammeters have to go inside the circuit. They have to allow the current to either flow through them or the electrons. So one of the things that we're going to have in 3 labs is resistors. And this is resistor code and how to read one. So for our virtual labs, our resistors will really only have 3 colors, but I'm going to show you with the 4th anyway so that you can see this. When you buy a pack of resistors, for example, here's one, you can see it says understanding the color code. It says black, brown, red, orange, yellow, green, blue, violet, of course purple, gray, and white. It's for the 1st and 2nd color. Then the 3rd color has a different thing. It's not a color, it's a multiplier. 1, 2, 3, 4, 5, 6, 7, 8. Well, those wouldn't necessarily work for us. And then we have what they call tolerance. In other words, how well it'll stay within the range you want. So when you buy a resistor, it's cheaper to have no tolerance, or the 20%. It's more expensive to have the gold. It just costs more. It means it's a more precise resistor. So let's see how we use this. So let's just say, and you're going to have to do this so on a number of these. Let's just say I have a resistor. First of all, gold, silver, they're always at the end. They're always last. So if you look at a resistor, and again, you're going to be doing it virtual, so it's going to show them the right way. That's going to be the last one. So basically, we're not going to use that too much, but I am going to still show you how. So here's the way this works. You write down the 1st color, then the 2nd color. You don't add them, subtract them, or do anything. You just write them next to each other. And then you say times 10 to the 3rd color, and then plus or minus the 4th. So let's do blue. I go through my chart, blue is 6. I write 6. My 2nd color was green. It's 5. It's literally 65, not 6 plus 5, not 6 times 5, just 6 plus 5. Times 10 to the, no, my 3rd color is brown. If I go to brown, it's 1. So it's 10 to the 1, plus or minus, and my 4th color was gold, which is 5%. All right, so let's work this out. 10 to the 1 is just 10. Remember, 10 to the 0 is 1. This is 65 times 10. That is 650 plus or minus 5%. And again, our virtual labs, we're just going to stop right there. We won't be using the 5%, but let's just make sure you know how to do this anyway. So how do I find 5% of something? Well, I go 650. Oh, let me clear this. 650 times 0.05. If it was 10%, I put 0.1, and that is 32.5. So 650 plus or minus, I live in a noisy area, ignore that. So if I take 650 minus that, I get 617.5 ohms up to, if I add it, then I get 682.5 ohms. This is what tolerance means. It means if I bought this resistor, that I'm okay with it being in that range. And that's all I need to have. So what we're going to do is we're really going to just do this. This is going to be, we won't, in our virtual labs, we really won't have this on here. Even though they'll show a 4th one, we're not going to figure out the percentage. So we would just call this a 650 ohm resistor. And we're not going to worry about tolerance because we're doing this in the ideal. All right, so we're going to do some practice problems using Ohm's law and the current formula. And then we're going to start the virtual lab on ohms and figuring out how we measure these things. All right, thanks everybody.